This lesson is about variation of parameters, and I'm going to sprinkle in a little undetermined coefficients. And we're going to learn how to solve the non-homogeneous system of equations. X prime, that's vector x prime, equals matrix A times vector x plus some additional vector function f. For f, a non-zero vector. See, in the last lesson we learned how to solve the homogeneous system. Now this is non-homogeneous. And the method is variation of parameters. And that's similar to what we did in Unit 3, Lesson 5. I'm going to sprinkle a little bit of undetermined coefficients at the end, and you might actually wind up preferring that method. But there is a connection between the solution of our non-homogeneous system and the solution of the homogeneous system that we did in Unit 4, Lessons 3, 4, and 5. Remember, sometimes they had distinct eigenvalues, sometimes repeated, sometimes imaginary eigenvalues. That made things a little more of a challenge, but we got through that all right. Well, when we solve that homogeneous system, we get a solution of the form vector x bar is a constant times x1 plus a constant times x2 plus blah 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 plus another constant times x sub n, right? All those in between, where x1, x2 up through xn are solutions of the system that are linearly independent, and the c sub I are just constants. So we've done that. We've learned to do that in those 3 lessons of Unit 4. So another way of writing this solution is to say, well, it's c1 times this vector plus c2 times this vector plus c3 blah 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 blah, blah plus c sub n times this vector. And if I wrote that out, this is an n by 1 matrix. But that n by 1 matrix can be written as a square n by n matrix times an n by 1 vector of constants. It would look like this. X equals, here's our matrix of functions times our vector of constants. Look, if you multiply this out, x11 times c1 plus x12 times c2 plus blah 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 plus x1n times cn, and that's what we have here in the top row of this square. Actually, it looks like a square matrix, but this is really a vector. But here it is, a square matrix times the vector, and that's the same as this. And so it's the same as this, our general solution of the homogeneous equation. So this special matrix here has a name, and it's called the fundamental matrix. So the square n by n matrix with columns that are linearly independent solutions of the homogeneous system x prime equals ax is called the fundamental matrix of the system. So the notation is usually phi of t, phi for fundamental, I guess, times constant vector c. So phi of t is the fundamental matrix whose columns are solution vectors given above. Note, it's always non-singular. Now, why would that matrix always be non-singular? Pause and think through that. Resuming from that pause, it's non-singular because its Wronskian is non-zero. If its Wronskian was 0, then those vectors, these vectors, this one, this one, this one, they wouldn't be solutions or linearly independent solutions of the system. So that matrix is non-singular. And of course, phi of t would be equal to a times phi, since each of the column vectors xi satisfies this equation. So how about that for interesting? And by the way, the multiplication would be compatible because phi of t is also the same size as square matrix A. So, as before, we get the solution to the non-homogeneous of the form x equals xc, the solution of the homogeneous, plus xp, if you want to call it the particular solution, and that would work. As in earlier lesson, Unit 1, Lesson 7, Unit 3, Lesson 5, we will assume that the solution xp that we seek is of the form phi of t times some vector u of t, but it's not a vector of constants. It's some vector of functions, u1 of t, u2 of t, blah, 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 and then the fundamental matrix, 5, and the fundamental matrix. So fundamental matrix times vector of non-constant functions. Of course, if it was a vector of constants, it wouldn't work out, because since it's a solution of the homogeneous, we'd never be able to get the f out of it. So we're going to assume our u of t is some other vector. Multiply it, of course, by our fundamental matrix. It's kind of like when we found, was that Unit 3, Lesson 1, you got one solution, then you can assume the other one is some function times that solution, right? And that always worked out for us there. And so we're going to do the same thing. So anyway, it must satisfy this equation. So if it satisfies this equation, then x prime, which remember, if this is what x is, we've got to use the product rule. So first d second plus second d first. Well, I have it d first times second because matrix multiplication would only work that way. And that equals a times our fundamental matrix. So a times our fundamental matrix times u of t, right? Because that's what we're saying the solution is, plus our f. Since we know that phi equals a times phi, because after all it's a solution of the homogeneous equation, then this simplifies, okay? I'm going to replace this with phi prime. So that means I'm replacing it with this. So what does that mean? In other words, I'm replacing a phi with phi prime. See, replacing a phi here with phi prime here. There we go. Now I think you understand. And what you see here, look, this and this, there they are on opposite sides of the equation, so they disappear. So phi times u prime of t equals f. And left multiplication by the matrix phi, which is non-singular, so we can do it, gives us the fact, in other words, multiply this side by phi inverse, multiply this side by phi inverse, we got u prime equal to phi inverse of t times f. Well, that's kind of nice. See, phi inverse times phi will give us an identity matrix. Identity matrix times u prime. u1 prime is just surely u1 prime. So how about that? So the inverse may be hard to find because, remember, phi is a matrix that has entries that are functions, but we can do it. There's an algorithm for those who must do this by hand. Look up the Gauss-Jordan method for finding a matrix inverse with row operations if you wish. But once we get there, we'll do an example in a minute and I'll go through that. But once we get there to here, right, then integration will find us our vector u. And xp, recall xp was some u times our fundamental matrix. So there, see, u times our fundamental matrix. So that means our fundamental matrix times, and here's how we find a u, by integrating this, right? So the solution of x prime equals ax plus f by variation of parameters is the complementary solution plus a particular solution. Here's the complementary solution, or the solution of the homogeneous, if you want to call it that, plus our xp, which is phi of t times the integral of phi inverse t times f. That's going to be complicated, and it won't take too many of these to make a dozen, ha ha ha. And so we'll do an example next.
Stretch out with your feelings.
Okay, we'll stretch out with our feelings and we'll nail it.